In part 3 of our reactions of alkenes, we're going to go over hydrohalogenation, which is exactly what it sounds like. We're going to add a hydrogen and we're going to add a halogen at the same time to an alkene. With hydrohalogenation, we learn for the first time about Markovnikov's rule. All right, so hydrohalogenation, as with the other reactions of alkenes, is also an addition reaction. So you can expect that the double bond is going to be broken, and we are going to be adding something to the carbons that were involved in the double bond. So usually we're using hydrogen halides because it's a hydrohalogenation. So this would be something like chlorine or bromine or fluorine or iodine, something that has a hydrogen attached to it as well. And these will add easily to the space where the double bond was. It does not require a catalyst, so we'll just show an arrow with nothing above it. So your hydrogen atom is going to bond to one of the carbons involved in double bonds. Remember, we're breaking this double bond, so now we have a spot to bond on each of these. So the hydrogen will go to one carbon, and the halogen will go to the other. This produces a haloalkane, okay, or an alkyl halide. We now have single bonds, so it went from being unsaturated with hydrogens to saturated. So it's a single bond, it's an alkane. From an alkene to an alkane, just like every other addition reaction we've been practicing. Let's see one in action. Cyclohexene reacts with HBr. Okay, there's my cyclohexene. And here is my H. And I'm going to draw the line between these because, again, it helps my mind to see that one of this, the hydrogen, is going to go to one carbon and the bromine is going to go to another. So for this reaction, we break the double bond, and that leaves a position on the carbons involved in the double bond, leaves a position for the hydrogen to bond to one carbon and the bromine or the halogen to bind to the other. So we wind up losing our alkene. We have, oh, these are just terrible cyclohexanes. So we've lost our double bond. It is now cyclohexane, and we have our bromine on one carbon and our hydrogen on the other. Now, truth be told, we don't normally show hydrogens when we're drawing a skeletal structure. So the more appropriate way to draw this would be simply showing the bromine coming off of that position. Does it matter that you did it in the bottom right-hand corner? No, it doesn't matter where you put the bromine. What matters is that you do the reaction right and that you name it correctly. So this would be bromocyclohexane. So we went from an alkane to an alkyl halide. I would not show the hydrogen. Are you going to be marked off the first time you do this? Absolutely not if you put the hydrogen on there. I will mark that that's unnecessary and you don't need to show that in the future. The example that you saw on the previous slide was an example of a hydrohalogenation for a symmetric alkene, meaning once I break that bond, it doesn't matter which carbon I put the halogen on and which carbon I put the hydrogen on. No matter which one I choose, I'm going to wind up with the same molecule. Oftentimes, however, we're working with asymmetric alkenes, meaning it does actually matter which side you put the bromine on versus which side you put the hydrogen on. You're not going to get the same molecule. So we have a rule to help us remember which carbon in the double bond gets the halogen and which carbon in the double bond gets the hydrogen. We call that Markovnikov's rule. So when you add a compound to the double bond, the hydrogen is going to bond to the carbon in the double bond that has the most hydrogens. A quick and easy way to remember this is the rich get richer. And this only applies to asymmetrical alkenes, meaning you would get a molecule with a different name, an alkane for a result, based on where you put the halogen. All right, so let's take a look at this example. We know we're going to break the bond. We know that either this carbon or this carbon is going to get a hydrogen or a chlorine. So according to Markovnikov's rule, we have to look at the number of hydrogen atoms on each carbon. So let's use different colors. This first carbon in green has one hydrogen coming off of it. This second carbon in red has one 2 hydrogens coming off of it. So according to Markovnikov's rule, your hydrogen atom is going to bond to the carbon of the double bond that has the most hydrogens already. The rich get richer. Well, this carbon in red already has 2 hydrogens. It has the most out of those 2 carbons. So I know I'm going to add my hydrogen to that carbon, and therefore my chlorine goes to the other carbon in the double bond. So let's rewrite this. Okay, so let's do it this way. We already had this structure. Okay, so we know that we are adding 1 hydrogen to the side that already had a lot of hydrogens, and we're adding the halogen to the side that did not. Okay, so to name this, we're going from an alkene to an alkane. This is a 3-carbon parent chain, so I know that this is propane since it's an alkane with single bonds. No matter which way I count this, it is still 2-chloropropane. If I had put it on the wrong carbon, if I had put it on this one instead, it would have been 1-chloropropane. It would have been incorrect. So it does matter which side you put that on. Let's practice with Markovnikov's rule. All right, we have 2-methylpropene reacting with hydrochloric acid. So I'm going to start with my double bond here. And I know I have a methyl group that takes care of propene. My methyl group is coming off of the 2nd carbon. So this carbon in the middle doesn't need any hydrogens. I'm going to give 2 here and 3 here. Okay, so looking at this, we're going to add to it HCl, and you thought you wouldn't use naming acids again. All right, so we have a hydrohalogenation. We are going to add the hydrogen to the carbon in the double bond that has the most hydrogens already. So looking at the carbons, this carbon has 2 hydrogens. This carbon has 0 hydrogens. The rich get richer, so I am going to add this hydrogen to the side to the carbon that already has the most hydrogens. The chlorine will go to the other carbon in the double bond. Don't forget that we break that. So let's go ahead and redraw this. So I'm just going to draw this in the complete structural formula. I think it's a little bit more helpful to see. Okay, so we added the hydrogen to the carbon that already had a lot of hydrogens, the rich get richer, and we add the chlorine to the other carbon in the double bond. If we were to name this, this is a propane, because now it's an alkane, and we have a chlorine group, and we also have a methyl group coming off the 2nd position. So now I need to alphabetize. Chlorine comes first alphabetically, 2-chloro, 2-methyl, propane.